going to have a look at implicit differentiation when my camera gets in focus. There we go. Okay. This is where you have a curve which is defined with x's and y's that you can't separate. So usually we differentiate things that look like this. Y equals tan squared x. Your y is on this side of the equation, so you can just differentiate this nice and easily. What if we can't separate the y's? Well, before we look at how we differentiate this, we're just going to consider what we actually mean when we differentiate usually. Because the one way that people misunderstand this is they think that dy dx means I have differentiated and this is what I get. However, if we look at a really simple example, when we differentiate this, we differentiate both sides with respect to x. So what we actually do is we say that I'm going to differentiate both sides with respect to x. Just like when we usually have an equation, as long as we do the same to both sides, we know it's still equal. We're doing exactly the same here. Well, we know how to differentiate x squared with respect to x. That gives us 2x. But now we're faced with the question, how do we differentiate the left-hand side? How do I differentiate y with respect to x? Well, y is a function of x. We can't do that. So we just write that we have differentiated y with respect to x. We just don't tend to write the brackets there because it looks cumbersome then. So what we're actually saying here is differentiate both sides of the equation with respect to x. We just can't simplify the derivative of y with respect to x, so we leave it like that. That's going to help us understand how to differentiate this. So again, we'll differentiate this with respect to x. So again, I'm differentiating each term as I go with respect to x. This term here, x cubed, that's easy to differentiate with respect to x. 3x squared. Now I'll need to think about this term here. How do I differentiate 4y squared with respect to x? I can't do it because y will depend on what the x value is. So we're going to use the chain rule to help us here. What we're going to do is we're actually going to differentiate 4y squared with respect to y. That's nice and straightforward. I know I can do that. And then if I use the chain rule to multiply by dy dx, remember, like we saw it before, it's almost as if the dy's cancel out. Remember, it's not strictly speaking a fraction, but it certainly helps you remember it. Okay, so we can now do this. I can differentiate 4y squared with respect to y. And dy dx, well, I can't simplify that, so I'll leave it as that. Cool. So I now know that the derivative of 4y squared with respect to x is 8y, differentiate it as per normal, times by the power, reduced to the power by 1. But then I have little dy dx at the end of it. And day to day, that's how you're going to do it. You're not going to worry about using the chain rule as such. You can just think of it as differentiate it as if it were an x, but then just write dy dx at the end of it, and that'll be sufficient. Okay, now we want to differentiate this one. We have to notice here though that we have two functions multiplied together, u, v. Whenever we have the product of two functions, we require the product rule. So I'm just going to put a little side note over here. The derivative of u with respect to x. So differentiate x, I just get 1. When I differentiate y, remember I differentiate it as per normal, that will just go to 1. But then I must make that little note, dy dx, which we know comes from the chain rule, but that's how we'll think of it day to day, and we can just get rid of the 1. And then I can just use the product rule. So minus 3 lots, because I've got 3 lots of my product rule, u dash v, minus 3 lots also of v dash u. Sometimes this catches people out because they expect the dy dx to be on the term with the y in it. However, remember that we get the dy dx by differentiating the y. And then finally, we're going to write the derivative of 12 equals 0. Notice that I've not written dy dx equals. I'm not saying I've differentiated this dy dx equals. I'm just differentiating each term as I go, and that produces my dy dx's whenever I differentiate a y. The main mistake on this is people write dy dx equals because they've misunderstood the notation. Okay, but we still do probably want to know what dy dx equals. So in order to get that, we're going to gather all of our dy dx's on one side, anything without a dy dx on the other side, and just make it the subject of the formula. So grouping our dy dx's, 8y minus 3x, and grouping these over here. And then dy dx is equal to 3y minus 3x squared over 8y minus 3x. So we've found dy dx from an implicitly defined function. We'll just have one more look at another example of this. So using this function here, we'll differentiate it and then we'll just do another few steps which you may meet in questions in an exam. Okay, so again, differentiate each term as you go with respect to x. Requires a product rule. So I'm going to get 2y. Maybe you want to put your little note over here just to make sure that you remember when you differentiate y, you get dy dx. Differentiate as per normal. But I've differentiated a y, so dy dx. Make dy dx a subject. And then divide through. I can probably cancel a factor of 2 here as well. Okay, so we've got our dy dx. Now we're just going to imagine there's a part B to this question. Find where the gradient is minus 2. Okay. So I want to try and find where on this curve, on this implicitly defined curve, is its gradient equal to minus 2. Well, we know when we want to find where a function has a gradient, I can just put it into the original equation, into the derivative, sorry. So that's what I'm going to do. I'm going to say that my gradient, which was given by dy dx, I know my gradient is minus 2, and also that the derivative is equal to 2 minus x minus y. Just like we would have done at AS, once we know the gradient, we can just set the gradient function equal to the gradient. Okay, let's just rearrange and simplify this then. So I'm going to get minus 2x minus 4y is equal to 2 minus x minus y. Let's just make x a subject for ease. So I'm going to get the, bring the x over here, x is equal to minus 2 minus 3y. Okay, so we've made x a subject, we know that x is that. However, that's an entire line. We didn't have a sketch for this, but the sketch of this would actually look something like that. It's an ellipse. But I've been told that my ellipse has a gradient of minus 2 somewhere on that line. How do I find the actual points? Well, what I'll need to do is I'll need to look at this and go, so that is some straight line, something like this. It's going to be a terrible drawing, but I apologise. Something like that. Because I know it has to be on that line, somewhere on that line is where I have a gradient of -2, but I also know the point must lie on the original curve. So what I'm actually looking for here is intersections between a line and a curve. That means simultaneous equations. It must be on this ellipse and on that line. So I can take my x and I can substitute it in. Okay, so let's do that. So I'm going to get -2 minus 3y squared plus 2 lots of -2 minus 3y times y plus 2y squared. Let's get rid of that little sketch. Minus 4 lots of -2 minus 3y equals 12. You can see that this is just going to give us a quadratic. We can expand and simplify this and then get the y values and substitute in to this equation, the simpler equation, to find the corresponding x values. Okay, we'll just do that. It's a bit of algebra, but it's not too hard. You said unable to do arithmetic. I'm just going to double check that before I move on. 4, 6, 12, 9, minus 4y, minus 6y squared, plus 2y, plus 8, plus 12. Cool, that should be good. And now we can just tidy this up. So I've got 4 and 8 is 12. I've got minus 6y, minus 4y. So I've got 5y squared. And then I've got 12y, 8y, 20y. And all of my constants have cancelled out. That's quite nice. Dividing through by 5. Pull out the factor of y. I can see that I get y values of y equals 0, y equals -4. Substituting those into here, that will give me x equals -2. That one into there, 12 take away 2 is 10. I've got my 2 coordinates. Okay, so key steps to that. Differentiate implicitly, first of all, one term at a time. Whenever you differentiate a y, you need to put a dy dx at the end of it. And remembering the product rule if required. Make dy dx a subject. Then, if there's a second part to the question, find where the gradient is 2. We set the derivative equal to 2. Simplify. Maybe you can just then find the value of x or the value of y, but it's more likely to be an equation. Remember then that you've got simultaneous equations. This line must intersect with that curve. Substitute in your x or your y, solve for x or y, and then substitute back in to your simpler equation to find the corresponding x values or y values if you've done it the other way. Okay, hopefully that makes sense.